Right. Yeah, in this video, we are going to talk about the principle of conservation of energy. Now, the principle of conservation of energy says that energy can neither be created nor destroyed, but it can be changed from one form into another. Now, in the last video, we talked about different forms of energy, like there's potential energy, kinetic energy, heat energy, light energy, sound energy. Okay, there are 9 different forms of energy that we discussed. And since energy cannot be destroyed, it must change from one form into another. Now, we're going to consider a diver. He climbs up onto the platform, diving board, to a height of 10 meters. So when he's 10 meters above the ground, he has got potential energy. And potential energy is given by its mass times gravity times height. And the mass of the diver is 80 kilograms. So its potential energy is going to be 80 times. Now remember, gravity is 10 newtons per kilogram, which is 10 newtons, times by the height, which is 10 meters. So 10 times 10, now that comes to 8,000 joules. So he's got a potential energy of 8,000 joules. That's 8,000 joules of potential energy. Now, when he's standing still on the diving board, his kinetic energy is 0. He doesn't have any kinetic energy. Now, what happens when he dives? Now, as he's diving, okay, we can draw him something like this. And then just before he enters the water, so as he comes down, now when he's halfway, he will have lost half of that potential energy. Now that potential energy, so his potential energy is going to be half of 800,000, which is 4,000 joules. Okay, what has happened to that energy that is lost? Now that has been converted to kinetic energy. So that means that 4,000 joules of potential energy he's lost is converted to kinetic. So you'll have 4,000 joules of kinetic energy. Now, as he comes down, he's losing more and more potential energy and is changing it into kinetic energy. So his potential energy at the ground level will be 0, and his kinetic energy will be 8,000 joules. So he hits the water with an energy of 8,000 joules, which is now what happens after he hits the water? All that energy is changed. Now what form has it changed into? Well, it changes into heat and sound. Okay, you'll hear a splash. It will change into heat and sound. So the energy changes. Okay, we say that its potential energy is converted to kinetic energy, to heat, to sound, plus heat. Okay, so this is the one example of an energy conversion process. Now, another one I'm going to consider is, okay, another example is the steam engine. Okay, a steam engine converts which form of energy to which? No, the steam engine burns coal or oil, which heats the water up, which makes the steam. So, what sort of energy does the coal have or the oil have? What the coal or oil have chemical energy. Okay, so we say that the chemical energy of coal, uh, that's converted into what? No, we heat the water up. Okay, that's converted into heat energy. Heat energy. No, but when we heat the coal, it produces steam. The steam drives drives the engine, okay, which makes the wheel move. So that is converted into kinetic energy. I'm going to write K for kinetic energy. No, kinetic energy of engine. Okay, plus also not all the chemical energy is converted into kinetic energy. Okay, some of it is wasted as heat and sound, plus heat and sound, plus sound. Okay, so this is another energy conversion process. Now we'll just do a few of these examples, okay, just to illustrate the point. The next example which we are going to do is the human body. Okay, what sort of energy do we convert? Well, I can move around. I have a body temperature which is constant. So I've got heat energy, I've got kinetic energy, I can speak, I have sound energy. Now, where does all this energy come from? Well, it comes from the food that I eat. It's the chemical energy of the food. So we say a chemical energy No, this is what gives us energy to keep my body temperature constant. So it produces heat. The chemical reactions in my body produce heat. So this is converted into heat energy. Plus, I also have energy to move around, plus kinetic energy, plus sound energy. Okay, sound is a form of energy. Okay, so a human body converts chemical energy to heat energy, plus kinetic energy, plus sound energy. A coal-fired power station. No, a coal-fired power station. It converts from chemical energy of the coal. Okay, when we burn coal, the coal changes from chemical energy to heat energy. We heat the water, which turns into steam, and steam drives a turbine. It's the kinetic energy of turbine, and the turbine drives a generator, which produces electrical energy. Okay, so this is how um, a coal-fired power station. No, coal is a fossil fuel. No, it can be coal, oil, gas, or nuclear. Okay, they all work on the same principle. So we say that the chemical energy of coal uh, is converted into heat. Okay, so when we burn the coal, it produces heat energy. So we have heat energy. Uh, of steam. The steam drives a turbine, okay, which changes to kinetic energy of turbine, and the turbine drives a generator, which produces electrical energy. That's the generator. No, this works for all the other uh, forms of power station. Not only coal, but oil and gas and nuclear. Okay, so we can write here coal or oil or gas or nuclear. Okay, so they work on the same principle. Okay, these are fossil fuels plus the nuclear. No, we can use oil to heat the water to make steam, or we could use gas or nuclear energy. It's exactly the same thing. The nuclear energy produces heat. The heat uh, is used to heat the water to make steam. The steam drives a turbine. The turbine drives a generator. Okay, so you get electrical energy generated. Uh, so all the power stations work on the same principle. Now, except for hydroelectric. No, a hydroelectric power station hydroelectric power station. Okay, how does that work? Now, this uses the energy of the water. Now, what happens is that you have a dam. There's water. There's a lake behind the dam. So the water here is at a higher level, okay? Then it's allowed to drop. Now, as it drops down, it loses potential, and the water has got potential energy here. Okay, so we said this has got potential energy of water. Okay, it's converted into kinetic energy when the water is moving. It's kinetic energy. So we have kinetic energy of the water, which turns the turbine. Okay, this is a turbine, which then drives a generator. That's generator. That's a turbine. Okay, so what happens is, this is dam. So we say potential energy of water, it changes to kinetic energy in the turbine, which changes to electrical energy in generator. Okay, so we say this is the potential energy to kinetic energy to electrical, okay, generator. Okay, let me write generator properly. Generator. This is electrical. Okay, the turbine has got, so potential energy of water converted into kinetic energy of the turbine. The turbine drives a generator which produces electricity and is turned into electrical energy in the generator. So this is another example of energy transfer. So there are many other energy transfers, okay, which you can find, but we can't go over all of these in this short video. Now, the next thing we're going to talk about is Sankey diagrams. Or energy transfer diagram, okay, or you can call them or energy transfer. No, what we do in the Sankey diagram is that the thickness of the arrow drawn to scale represents the energy. Okay, we will do this with an example. Filament light, no, example, filament light bulb. No, the old light bulb which have lamp filament, okay, they are really wasteful of energy because first the filament gets hot, so most of the energy is wasted as heat. But the useful energy that we want from the light bulb is the light energy. Okay, so what happens is if we have, I can represent the thickness of the arrow can be represented by the energy is represented by the thickness of the arrow. Okay, so what we do is we find that if this is 20 joules, now I can draw this to scale. Say I can draw this 20 centimeters. Now out of that, only 1 centimeter is the useful energy. This produces light. Now this is the useful energy. Because that's what we want. From a light bulb, we want the light energy. We don't want any other form of energy. But unfortunately, what happens is that most of the energy is just wasted as heat. So I can draw this arrow like this. And you'll find if this is the 20 joules of energy that we put in, um, you'll find that only 1 joule of this give you the light energy, and 19 joules is wasted as heat. Okay, no, it's a very, very inefficient device. It wastes lots and lots of energy. That's why we use the low energy bulbs, okay, which waste less energy. So we can draw the diagram, okay, by drawing the thickness of the arrow to represent 20 joule, okay, and then the thickness of this arrow will be very thin. So if this is 20 centimeter, there will be only 1 centimeter, and this will be 19 centimeters across. We can represent it like this. We can define the efficiency Now, the efficiency is defined as the useful energy output divided by the total energy input times by 100. Okay, this will give us the percentage efficiency. Now, this is the formula that we use for percentage efficiency. So in this example, this is the energy input, okay? We say electrical energy input. Okay, this is how much energy we are putting in. That's 20 joules. This is 20 joules. And the energy, the useful energy we're getting out is only 1 joule. And the rest of the 19 joule is wasted. So the efficiency of this process will be useful energy output is only 1 joule. We say percentage efficiency equals 1 divided by the total energy that we put in, which is 20 joules, So it's 1 divided by 20 times by 100, which is 5%. Now, this light bulb is only about 5% efficient, which is very, very bad. So we say only 5% of the energy is used. The rest of the 95% is wasted. So this is an example of the use of energy and efficiency. So you need to you can draw this Sankey diagram for all sorts of different devices where energy is used in different ways. But we can't give any more examples, okay? Otherwise the video will be too long. So we'll end this video now.